For this next one, be looking at the service API and specifically doing batch optimization at the very end. And in between that, we'll cover a few things like saving our data in the state of our optimization experiment, and some mention of connecting to a SQL database. So here we have our, instead of the loop API optimize function, we'll use an AxClient class. And we'll use the Hartman-6 objective function, the usual utility helper functions, and we'll instantiate an AxClient using our AxClient class. And I'll note that you can pass in some arguments here, like a custom generation strategy. There's some useful documentation about that in the documentation, random seed, and so on. Then what we need to do, you'll notice a similar syntax compared with the loop API, but instead here we say AxClient.create experiment, and then we pass in the name of our experiment, our parameters that help to define the search space, as well as our objective name to minimize parameter constraints and outcome constraints. And as we did before, we'll define our evaluation function, our objective function that will take a dictionary of our parameters mapping from the parameter names to their values, and then extract those values, extract it into a NumPy array, and return a dictionary of our objective function name corresponding to our objective function value and the standard error, and then our other outcomes. Then instead of just specifying the total number of trials, here we'll dig a little bit deeper. We're going a little bit lower level in running a for loop across the number of trials that we want to run. So we'll say we'll run 25 trials, and then we'll split the process into really three different steps. One where we get the next suggested experiment, another where we evaluate our objective function, and then finally where we report it to the AxClient, the completion of the trial. And by default, Ax restricts how many trials you can run in parallel, which I think is generally 3 when you're running Gaussian process optimization, and then it looks like 12 when you're running the initialization of Sobel points, which is very typical for optimization algorithms when you're doing active learning, to start out with this quasi-random sampling of the space and then start fitting a model, because essentially you don't, if you try to use the Bayesian optimization from the get-go, then you don't have any information to begin with. You have no prior information, and so you're not really. You may as well randomly guess or do quasi-random search for that, and that's its own whole topic in itself. So then we can talk a little bit about viewing existing trials. So we can access the generation strategy and then this trials as DF or data frame property here, and get a look at the different parameterizations and the status of the trials, which model was being used to generate the trials, and then the trial indices. Now, whereas the optimize function just returned the best parameters and the values and the experiment and the model, here we use our instantiated class of the AxClient and the get best parameters method of that class. But essentially we have very similar outcomes here, just a slightly different API for how to go about that. And we can take a look at our means and covariances, and see that we're doing a fairly decent job in optimizing, getting low values compared to the true minimum of the Hartman-6 function. Like before, we can use some plotting functions. In this case, AxClient has a method called getContourPlot, um, which you can pass different parameters in for what you want to be plotted on the x-axis and the y-axis, and which metric or objective or outcome you want to be plotting on there. And that's shown here, where you can plot other values for that. And then we also have the optimization trace, where we can pass in the objective optimum if that's known in advance, which for any chemistry or material science optimization task, most physical science tasks, you're looking for an objective. It's not already known, but in this case where we're doing kind of some benchmarking or using an analytic function where we know the true minimum, it can be helpful for visualization to see how closely we've progressed towards that optimum. And we also have the model change shown here as well, with the green dashed line, meaning that is when it transitioned from doing quasi-random Sobel sampling to the Gaussian process expected improvement model. In this next part, we'll be looking at saving and reloading the optimization. Now, this is very important for reproducibility, as well as just for staying organized, keeping track of things, making sure you don't lose the data, and that you don't you can keep a very orderly history. So you can use AxClient.save to JSON file, and you can specify your own file path here. And then what you'll do is use AxClient as the class dot load from JSON file. And again, you can specify a custom file path here to get your restored AxClient, or essentially your loaded AxClient. And then there's some ways that you can connect this to a SQL database backend. They have some instructions on the Ax website for how to do this. And then you pass the appropriate URL into this DB settings class, and that kind of connects things under the hood for you. Now, there are a few special cases that are worth mentioning. One will be when there's an evaluation failure. For example, let's say you're running a set of experiments in a chemistry lab, and the experiment fails partway through because of the specific combination of parameters you used. Something crystallized, but you never expected, you weren't expecting things to crystallize, and that affects your ability to measure the objective function. In other words, the experiment failed. Another case would be if you're tuning a machine learning model and you choose some, the model chooses some set of hyperparameters for the machine learning model that causes all nans in the model, or throws an error that was unexpected but happens only occasionally. In these cases, rather than trying to fix whatever the cause of this occasional error might be, or this unanticipated situation, one option is to log it as a trial failure. And what this will do is it ensures that the same trial is not proposed again. And that looks like this: AxClient.log trial failure, and you pass the trial index for the particular set of parameters that failed. And then you can also add custom trials. So everything that I've shown so far, the suggestions for next experiments are based on quasi-random sampling or Gaussian process expected improvement, or the Bayesian model. But oftentimes we have existing data that we want to attach to an experiment before we do optimization. If we've already spent hundreds of hours running experiments, and then we decide we want to start running the Bayesian optimization, attached trial is the method that we can use for this. So in a for loop, you can pass in the parameters that you already have recorded experimentally or from simulations, so forth, and then use after you used AxClient.attach trial, then you should be able to use AxClient.complete trial with the measured objective values for those. Here it talks about the keyword argument to AxClient of enforce sequential optimization. And this affects whether, so we'll read this here. We strongly recommend sequential optimization, generating a few trials, then waiting for them to be completed with evaluation data. However, if your use case needs to dispatch many trials in parallel before they are updated with data, and you're running into this error, all trials for current model have been generated, but not enough data has been observed to fit the next model, then you use this function. In other words, this allows you to move from the, for example, from the quasi-random model to the Gaussian process model before you've completed the total number of trials that were supposed to be done in the quasi-random one. And this also talks about some of the exceptions and how to handle them. So here we, by default, Ax will assign a max parallelism of, I think before it was 12 for the quasi-random Sobel search, and then 3 for the Gaussian process expected improvement model. But you can override this value using choose generation strategy KW-args during the create experiment. And if you take a look here, you'll see that it's now 10 and 10 for the quasi-random and the GPEI. Now, this is where we get into actual parallel batch running. In other words, we run batches of experiments, and within each batch, we run the individual experiments or trials in parallel. In this case, using multiple workers, CPU workers. And for this, one easy way to do this parallel processing is through Ray. So we import Ray, we initialize it with the number of CPUs that we're going to use, and ignore an error if we call ray.init again. In other words, if we run the cell twice, so it doesn't throw an error. And then we define a remote function here. And in this one, we're just taking a number, computing it square, and returning that value. And we use the decorator here at ray.remote. And then we can use a list comprehension here or a for loop if we wanted to. And then we call square.remote of our input value for x in range of 1000. And what this list comprehension is going to do is it's going to essentially create a queue that starts running those functions on the different parameters. And then the ray.get method is going to block the execution until those results are ready. So in other words, we're not going to move on to line 16 until ray.get has gotten all 1000 points here. And you can take a look and see that square results then has, if we look at the first 5 and the last 5, we have 0 squared, 1 squared, 2 squared, all the way up to our max. So let's take this simple example where we just computed the square of a number and apply this to parallel evaluation of trials within batches. So we'll have our batch size be 2, just for simplicity. This could be whatever you want. If you have more resources available, you can have higher batch sizes. We can have total trials as 11, instantiate our AxClient. Similarly, this time using the Brannon function, so just two dimensions here. We'll put our max parallelism override as our batch size. We'll switch our enforce sequential optimization to false, and then we'll define our evaluate function as a ray.remote decorated function, where we return again the objective name and then the function value here. From there, There are other ways that you could do this, presumably, but one way for batch optimization is to define your number of batches and set a counter for which iteration you're on, and essentially use your normal batch size up until your last batch, at which point you set your batch size to be the remainder, the difference between how many trials you wanted and how many trials you've already run. So here we'll get our trials using AxClient.getNextTrial. We'll unzip those into our parameters and our trial indices. We'll get that queue running with our evaluate.remote of parameters for parameters and parameters batch. And then we'll block until we get all of the results from the batch. Then finally, after all the results have been computed, we'll report the completion of those trials back to the AxClient, like so. So that was the Jupyter Notebook for batch optimization. And just to summarize a few things, we've got the use of the Ray framework to do some parallelization. There's also RayTune, which has some integration with the Ax framework, which allows you to use a slew of various optimization algorithms, including those in Ax. Not all the functionality, but a lot of the functionality that you'd be looking for that will do asynchronous optimization, which we'll be covering in a later tutorial. And to pull out some results here from a materials discovery case, a nice review put together by Raimundo Ariave and others. They looked at, or in this review, they discussed sort of results where you have a varying batch size and the average number of iterations it takes to reach some optimum value. With increasing batch size, the total runtime decreases, but the efficiency per individual worker decreases.